then I can do what to this? Well, I can differentiate it, right? It's not quite right to differentiate a function of n, is it? What would that mean? How do we differentiate? We take values of the variable arbitrarily close to the place we're differentiating, right? Can you do that with a discrete variable? You can't, right? But more on that in a minute. So here, but on the other hand, you're like, isn't that just the same thing? But you just made your x and your n into an x. I mean, okay, I did that. That's true. So that I can differentiate, because that's a continuous function, right? Thinking of x as a real variable. And if x is greater than 1, think about this. This guy is smaller than that guy, which means that this wins in terms of it being negative. What does that mean? If the derivative is negative, the function's what?
Going down.
It's going down. It's decreasing. And if the function's decreasing, that means that if you think about it, if n is less than m, then f of n is greater than f of m. It's decreasing. And then by consequently, a sub n is less than m. In other words, this if you see the function's decreasing, then the sequence to which it corresponds is also decreasing, right? And and then this is, and then I argue that in fact it's a bounded monotonic sequence, which means the limit exists, all right? So this is a kind of forced example, all right? Like, fine, it's true. But really, if you want to know what the limit is here, I don't use the recursive thing here, right? What do I do? Look at this. So to calculate the limit of here, we do what? We multiply by sort of the conjugate of this in some sense, replace the minus with a plus, do algebra, and we get to this, which goes to 0. So if you pay attention, did we need the bounded monotonic sequence thing here? We did not. So really, this argument right here, just this line of algebra would solve the limit. So at this point, I felt guilty for not having defined the limit infinity. Here's the definition of the limit being infinity, which I really don't need to write on the board. I think you would have known it. Whether or not I told you, you probably would have had an intuitive idea. This example, I explicitly prove the limit of n squared is infinity in view of that definition, all right? So there might be a problem in the homework where I ask you to prove the limit's infinity from the definition. I may or may not have actually put that in your homework. It's one of those things I was debating about whether or not I actually put it there, all right? Okay, the larger point here is this. If you have a function which matches the sequence, then, in other words, just what I just did in the previous example, right? F of n is equal to a sub n. In that case, there is a natural correspondence. The limit of the sequence is L if and only if the limit of the function is L. What does that mean? That means that we can steal from the calculus we know to calculate these limit sequences. All right? So in particular, I really just used that trick in the previous one. Here's a more in-your-face use of it. A sub n is inverse tangent, right? So I think f of x is inverse tangent x. Well, f is continuous on reals, and what's the limit? What's the limit as n goes to infinity of inverse tangent of n then? Well, it's the same as the limit as x goes to infinity of inverse tangent of x. Now, I know that the limit of inverse tangent, or arctangent if you guys like, is pi over 2 because I can graph it, right? We know that it's got that the tangent function flips on its side and it goes to pi over 2 as x goes to infinity, right? So if you're just sampling points in that, same limit, still pi over 2. So this is a welcome, like, you're like, this is better. You're not talking about epsilons and n's, right? Right? We're happy, yes? So I wanted to make sure I got to this today because this is really more where we live in here in terms of calculating limits, all right? I still need another. Tomorrow I have to prove, there's something I was supposed to prove today that I didn't get to, and it's in your homework, so I really should prove it tomorrow. Yep. All right, let's continue on here though. So what about this? You're like, wait a minute, flag on the play. Didn't you just tell me we couldn't differentiate with respect to n? Well, this is the thing, is like, it's just a letter. So I feel like all you need to do especially as engineering students, possibly future math majors. So once you're a future math major, beware that there are other professors who probably would be unhappy with me for doing this, but they can deal. So here, what I do is I just say extend n continuously. This is my license to think of n as a real variable. Your book, if you look at Stewart, what he does is he says, let f of x be x e to the minus x. And then he goes and he does L'Hopital's rule on f of x, blah, 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 blah. And at the end of all that, he's like, oh, and then by the transfer theorem, we go back to n. I just think, why bother when I could just teach you guys, you write at the start, extending n continuously, and then I can use L'Hopital's rule, like this one. So here we're like infinity over infinity type limit, right? So L'Hopital's rule says that's the derivative of the top over the derivative of the bottom if I extend n to be continuous. Differentiating, I get 1 over e to the n, which is 0, right? So in a battle of exponential versus polynomial, who wins? Always bet on the exponential, right? And so here's the things that you should know. Of course, the limit laws. Sum of the limits is the limit of the sum. Or difference. You can pull constant out. You can prove the limit of a product is the product of the limits if they exist. And you've got a quotient law for limits, right? These are the limit laws we saw before with x going to infinity in Calculus 1, right? And then the one that's more subtle, though, and actually more interesting is the squeeze theorem. Squeeze theorem says that if you've got 3 sequences, which you've got a middle sequence and an above and below sequence, right? And if the limit of the above sequence and the limit of the below sequence both go to the same limit, that follows the middle sequence must also limit to that. This we actually use to calculate some limits which are less obvious. All right, so for example, well, I better pick up here tomorrow. I don't want to blow through this stuff too fast, so I think I'm out of time. I got 5 minutes. I'll give you guys these 5 minutes. How about that? It's been a good day. It's a good time to stop here. I don't want to overwhelm you too much with this stuff.